discuss the KSZ effect, what that is, talk about H1 intensity mapping, the cross-correlation, which we compute a bispectrum, and then talk about the signal-to-noise estimates that we obtain with HIRAX and also with SKA. Thereafter, I'll discuss another aspect of my thesis, which was on calibration techniques with HIRAX, and discuss or compare redundant and quasi-redundant baseline calibration algorithms, and then talk about future work. Okay, so firstly with the the cross-correlation work, what we're interested in is the kinetic Sunyaev-Zel'dovich effect. So basically the Sunyaev-Zel'dovich effect is a result of CMB photons inverse Compton scattering of ionized electrons. And this is one of the secondary CMB anisotropies. So the result of this is, well, there's two Sunyaev-Zel'dovich effects that we usually spoken of. There's the thermal SZ and the kinetic SZ. So the thermal SZ probes thermal motions of electrons. The kinetic SZ probes the bulk peculiar velocities and basically bulk motions of electrons. They're both really interesting. The reason we chose the kinetic SZ, one of the reasons, is because we're interested in probing the evolution of baryons and finding missing baryons. So the missing baryon problem is quite well known. There are some percentage of baryons that are not accounted for, and they're believed to be in the warm hot intergalactic medium. So this WIM is basically, it's not a very hot region. So the thermal SZ wouldn't be ideal to use to find these missing baryons, because the TSZ, as it's called, is usually used to probe high density and high temperature regions, which the WIM is not. So because of that, the kinetic SZ is actually a much better probe for missing baryons. So I'll talk about the KSZ in more detail in the next slide, but the slide is basically just showing on a large picture what we're trying to do. So besides using the kinetic SZ effect, the other signal that we're interested in using is the H1 signal. So the KSZ is useful because it probes electron densities and bulk peculiar velocities. Free electrons trace baryons. And the velocity field is a large scale field, so it's unbiased by the local environment, which means we can probe diffuse baryon distributions. So all of that is great, but the problem with the KSZ signal is it's a projected signal, so it's, it accumulates information across redshifts up to reionization, up to and including reionization. So if you want to probe missing baryons at different redshifts, you need to use a signal that actually allows you to include redshift information, and that signal is the 21 centimeter signal. So yeah, that's basically the big picture. So the kinetic SZ effect is, well, this diagram describes it. So as I said, it's a CMB photon that scatters off an electron as shown in the diagram, and then you have a Doppler shifting of that CMB photon as a result. The equation is just a basic equation for the KSZ where tau E is your optical depth and V peculiar, your peculiar velocity, and then C is your speed of light. So the diagram on the left basically shows the KSZ autocorrelation power spectrum. Even though I said that we can't isolate the signal in particular redshift bins, what we can do is get a sense of how much KSZ signal is contained in the HIRAX redshift range. So the experiment that we focused on for my master's thesis was HIRAX. and the redshift range of HIRAX is about 0.8 to 2.5. So if you look at the diagram, you can see that the KZ signal between the two redshifts, well, in the redshift range that we're interested in, is sort of between the black and the green lines. So it shows that there is quite a bit of KZ signal contained in this redshift range that we're interested in. Okay, so one thing that we can look at, since we're using KZ signal and its convolution of the density and radial velocity fields, we can determine the dimensionless power spectrum or signal variance due to each of these velocity and density power spectra to see where the majority of our modes are, or sorry, where the modes dominate. So the peculiar velocity is very simply written in linear scales by the equation that's shown, where delta of k is your density field, and you have some k vector, h naught is your Hubble constant. And what you can see in the two diagrams is that again, we can take the left plot first, so the velocity power spectrum. The modes dominate on the angular scales and radial scales that are demarcated in red. And on the right, you have the density power spectrum. So you can see that both fields dominate in the same radial scales and different angular scales. So the velocity field, as I said, is a large scale field, which you can see from this diagram because it dominates at small angular scales. The reason that we don't consider the darker region at the top of the density power spectrum plot is because we ignore any modes greater than 0.14 inverse megaparsec, and that's due to nonlinearity. So we ignore radial nonlinear modes. So one of the challenges of the KZ effect is that there's primary CMB completely dominating it at low L, and then the detector noise is completely dominating at high L. So what I've shown in this plot is the primary CMB in red, the KZ signal in green. It's referred to as the Ostrika-Vishniak signal because we're only considering the linear KZ. There's an extension to nonlinear KZ, which I haven't implemented in my thesis, but just for clarity, that OV refers to Ostrika-Vishniak. And the blue line is the detector noise. So the detector that we use is AdvACT. We don't actually use it. We use the noise from that detector. So what you can see is that the CMB spectrum kills all the signal at low L, the detector noise dominates at high L. There's a small window, we can refer to it as a window, where the KZ signal is possibly detectable. So we're not actually interested in observing the KZ signal itself, only the cross correlation, but the KZ window that's demarcated here does come up in plots that I'm going to show with the cross correlation signal to noise. Okay, so now that we discussed the KZ signal, we can move on to the H1 signal. So there's different possible, well, you could use galaxy surveys, for instance, and cross-correlate that with the KZ signal. That has been done numerous times. But another option is to use intensity mapping, which is what we're planning to do with HIRAX. So H1 intensity mapping is really useful because unlike galaxy surveys, we are not interested in resolving individual galaxies. So H1 intensity mapping requires a lot less time and is a lot more cost efficient. the bottom plot just shows the H1 content of our galaxy, and the plot on the right is the 8-dish prototype of HIRAX that's at HARDRA at the moment. Okay, so with regards to the H1 signal, the equation that's given for H1 signal is in the block, where delta T21, which is your temperature fluctuation due to the 21 centimeter signal, is equal to the mean temperature times the dark matter density over density multiplied by your redshift space distortion factor. And I also give the noise specifications for HIRAX. So we're assuming a system temperature of 50 Kelvin. My results are assuming 1024 dishes, so that's going to be the full HIRAX array. We have 6 meter dishes. The frequency range is 400 to 800 megahertz, 1024 frequency channels, so 390 kilohertz per channel, and 15,000 square degrees for the survey area. So if you plot the HIRAX noise, which is shown on the right, you can, it's plotted against the 21 centimeter power spectrum for different Y modes. So the L and Y modes are observational coordinates, which are really useful to use in intensity mapping because we're not surveying individual galaxies. So the Y modes are calculated for particular redshift and frequency bands. So one important thing to note from this plot is the HIRAX noise and how it cuts off signal at high and low L, and that severely decreases our signal to noise, which I'll show you. Okay, so in computing the cross-correlation, initially you might assume that it's easiest to just take the KZ signal and correlate it with the density, the 21 centimeter density field. But that correlation gives you zero signal because the KZ signal is composed of 2 Gaussian fields, your density and velocity fields, and you're correlating that with a third Gaussian field. So you would have no signal from just a simple 2-point correlation. Rather, what we do is we include a fourth Gaussian field, which is the velocity H1 field. So it's a reconstructed velocity field. So what I show here is if you can construct a proxy for the H1 momentum signal in much the same way that you compute the KSZ signal. And this is basically just the reconstructed H1 momentum signal and the power spectrum that results from that. And you can see from the plot that it might not be too clear from the 2D plot, but if you were to sum over all the k-parallel modes and plot this as a 1D plot as a function of L, the H1 momentum signal peaks at the same L that the KZ signal peaked at that I showed in the previous slides. So, okay, I think that's everything I wanted to say now. So in terms of constructing the bispectrum, we consider it to be a bispectrum because even though we have 4 Gaussian fields, we're using 3 maps in computing the spectrum, the signal. We have the CMB map, density, H1 density map, and then a reconstructed H1 velocity map. So yeah, 3 signals. And you can see in the diagram on the left, you have a bispectrum triangle. So you have 2 long K modes. That's the density H1 mode and the KSZ momentum mode. And the short mode is the velocity H1. So that's because, as I said, the H1 velocity, or the velocity signal is a large scale signal. The linear velocity signal is large scale. So basically what we're doing is we're taking the three signals and correlating them within a box. So you can consider the universe to be constructed of redshift boxes, and then you compute the signal within each box and sum over the signal in each individual box. And in computing the bispectrum signal, I show the result for the signal plotted for the 700 to 800 megahertz frequency bin. Again, we're showing a 2D plot, so it's shown for different K-pop and K-parallel modes. You can see that the signal is dominant at large, angular, and radial scales. The angular scales matches that of the H1 momentum signal, which is expected because it's constructed in a very similar way. The radial scales are quite different. There's a lot of signal at low K-parallel modes. And this is unfortunate because we can't access K-parallel modes that are so small. So we only pretty much get up to about a K-parallel min of 10 to the minus 3. And with foregrounds, that's even worse. So a lot of the majority of the signal is actually inaccessible to us. Okay, so the signal to noise estimates with HIRAX, I showed the results for each of the 400 megahertz frequency bands. So just to remind you, HIRAX's frequency range is 400 to 800 megahertz. The HIRAX beam and CMB cuts out signal at the low K-pop, and then you have, the HIRAX noise cuts out signal at low and high K-pop. The CMB cuts out signal at low K-pop. So you can see that majority of the signal is contained within the KSZ window, which I showed at the beginning. As you go to lower frequencies, the noise cuts off more sharply at high K-pop, and that can be explained by referring to the plots at the bottom left. So this is the HIRAX noise plotted for each of the 4 frequency bands, and the blue curve corresponds to the 700 to 800 megahertz. So you can see that you have access to more high K-pop modes if you're looking at higher frequency bands. Okay. So the other experiment that we considered was SKA1-MID, so phase 1 of the mid-frequency SKA. So this experiment does extend to a larger frequency range, but since we're considering SKA and comparing it to HIRAX, we only consider the HIRAX frequency range when looking at the SKA experiment. So even though the frequency range is 350 to 1050 megahertz, we ignore a lot of that. So what's plotted on the right is the SKA curves for the interferometer, SKA1-MID interferometer, and for a single dish SKA1-MID experiment. So, and then that's compared to HIRAX. So you can see that the SKA1-MID dish gives you access to a lot more low K-pop modes than you would otherwise have access to with HIRAX. And the SKA1-MID interferometer gives you access to a large range of high K-pop modes. So it's seemingly useful. It is quite useful. But the SKA noise is also quite a bit higher than HIRAX within the KSZ window. So the black demarcated regions are the KSZ window. So this is the part where the signal to noise is most crucial. So it's difficult to tell how the 2 experiments will compare just based on these noise curves. We can also consider the 2D signal to noise plot with SKA. So you can see that if you compare this to the same frequency range that we had with HIRAX, so the 700 to 800 megahertz with HIRAX in the top left, and the SKA1-MID in 700 to 800 megahertz, you can see that there's a lot less signal within the frequency range, within the KC window, sorry. But there is also more signal with SKA outside of the KC window. So that's because the velocity modes, the radial velocity modes, are not suppressed by the CMB, the primary CMB. So essentially with SKA, what you have is access to a larger range of velocity modes than you would have with HIRAX. But again, the signal to noise within the window itself is still quite small. So here we can compare HIRAX and SKA by considering the cumulative signal to noise for each of the 4 bins, and we also include the effects of foregrounds. So foregrounds are frequencies, galaxy signals that are a lot higher in magnitude than the signal that we're interested in. So to sort of account for the effects of foregrounds, we introduce a foreground cut at k parallel of 0.01 inverse megaparsec. So we don't consider any k parallel modes smaller than that cut. And then the effects of that are shown in all of the dotted lines. So you can see that HIRAX and SKA, if you consider the blue curves in the top panel, they're very similar. So even though SKA has less signal to noise in the KZ window, as I said, the velocity modes give it a boost, give the signal to noise a boost so that the 2 experiments are comparable. More interesting is the effect of foreground. So you can see that the signal cuts quite a lot due to the foreground cut that we have to include for the k parallel modes. The results are essentially just 11, a total signal to noise of 11 for HIRAX and 11.5 for SKA. If you assume low foregrounds such that the foreground cut isn't required, and the signal to noise, if you assume high foregrounds, is 4.2 and 4 for HIRAX and SKA1-MID. This plot is basically just showing, again, the effect of foregrounds, but plotting the cumulative signal to noise as a function of k parallel, that's a typo, instead of k pop. So you can see that the dotted curves, again, are the foreground cuts, and the solid lines are assuming low foregrounds. And you can see that there is, again, a lot more signal to noise if you assume low foregrounds. Okay, so that's basically the cross-correlation work. And to segue into calibration, the theory is really easy to do, but in reality, we have to do calibration so that we can get the results that we expect with theoretical predictions. Also, calibration is really useful for foreground mitigation. So I'll just briefly talk about calibration. It's just discussing redundant and quasi-redundant calibration techniques that we're planning to implement with HIRAX. So firstly, I'll discuss traditional redundant calibration. So basically what redundant calibration does is, obviously it assumes complete baseline redundancy. So it assumes that your baselines are perfectly redundant. It doesn't account for any possible dish offsets or beam variations from one dish to another. It also doesn't require a sky model, which means that you can't do absolute gain calibration with redundant calibration. You can just sort of do relative gain calibration. The measured visibility equation is given as Cij, which is your measured visibility, equal to your gains. So G is your complex antenna gain. Y is your true visibility, and N is your noise. And then I and J are just subscripts for different antennas. So if you take the logarithm of this equation, which is your standard redundant calibration equation, then you get LogCal, which is an algorithm that takes the logarithm and then solves for the gains and true visibilities. So one thing that you can do with LogCal that's quite easy and useful is using least squares error to consider how calibratable your array is and how the positions of dishes affects your calibration. So the plot on the right just shows the results for a 16 by 16 array. And you can see that the most redundant baselines, which are situated in the circle around the center, have the lowest gain errors. The corner dishes that are the least redundant or contribute to the fewest number of redundant baselines have the highest gain errors. So this is plotted for the gain amplitude. We can extend this. So I know Warren did some work on array layouts. So this is basically using his results and the different arrays that he considered. And we just wanted to do a quick test to see how calibratable these array layouts were. So what you can see here is the effect that baseline redundancy has on gain errors. So there were five different array designs considered. There was the square that was shown in the previous slide, hexagonal array, HIRA array. I reduced the size of this so it's not as large as the actual HIRA. And then two other plots at the bottom that sort of subgrid. So you position 4 dishes together and then 2 meters apart, place another 4 dishes and so on. And well, that's the bottom left plot. And the bottom right, you have 4 8x8 arrays with 3 meters in between the left and right columns. Yeah, so the plot on the right just shows the redundancy versus unique baselines. So you can see for 3 of the array layouts, that's the square, the hex, and the HIRA-like. I call it HIRA-like because it's smaller than HIRA. So those 3 have roughly the same baseline redundancy plot or curve, with the HIRA-like having a slightly higher number of redundant baselines. And then the alternating and subgrid are the 2 layouts shown on the bottom left. They have exactly the same baseline redundancy curves. And basically you can see from this plot that it's not the number of dishes that matters, it's how you place those dishes in terms of what contributes most to a higher number of redundant baselines. Because as you can see in the table, the HIRA-like array has the fewest number of dishes. It's the only one that doesn't have 256 dishes, but it has the lowest gain error across the entire array. But yeah, this plot was really just to see if we were sort of breaking our ability to calibrate with any particular array. It's not recommended that you design an array just so that you have an increased number of redundant baselines. Obviously depends on the array layout that you choose, obviously depends on a lot more than that. But that was just to show some results that were with LogCal. But now moving on to something I think a bit more useful. The problem with redundant calibration, traditional redundant calibration algorithms is, as I said, it assumes complete baseline redundancy. If you want to be a bit more realistic, you consider possible non-redundancies in your array, and redundant calibration techniques like LogCal and LenCal, which I didn't mention, but it's also another technique that's used. They don't take this into account. So correlation calibration is a technique that was developed by John Sievers, and it hasn't been widely implemented as yet. So we're considering, we're just testing this out for HIRAX at the moment. It's an extension of traditional redundant calibration because it accounts for non-redundancies. It assumes some knowledge of the sky, so you can input some information of the sky that you already know. And the visibilities and the noise, the sky signal, everything is separated into redundant blocks. So you can control how redundant your array actually is, in a sense. So if, for example, you have a perfectly redundant baseline like you would in redundant calibration, your redundant blocks will just be organized exactly according to your redundant baselines. But if, for example, you input some dish offset, for instance, and your baselines are no longer completely redundant, then you can determine how redundant your baselines have to be for them to be considered in the same redundant block, if that makes sense. So yeah, increasing the number of redundant blocks if your array has really bad dish offsets is an option that's provided by CorrCal. So what CorrCal does is it computes a chi-squared and it minimizes that chi-squared and returns gain, amplitude, and phase errors. So, well, gain, amplitude, and phase recovered gain results. So the chi-squared is given as, well, the equation that's shown, where D is your visibilities, N is your noise covariance, H is your inverse gains, and C is your sky covariance or visibility covariance. So for the next two slides, I'm just going to give some results that show the comparison of LogCal and CorrCal. So these results are just shown for a perturbed array. The perturbation that we consider is 10 centimeter offsets in antenna positions, considering using an 8x8 array with 6-meter HIRAX dishes placed edge to edge. So you can see that, well, with LogCal, we don't, since LogCal can't account for any dish offsets, the results are expected to be worse than with CorrCal. So these results on the slide are shown using unresolved point sources. We compute the mean and standard deviation of gain amplitude errors using 500 noise realizations, again, for the perturbed array. And I didn't give the results in this presentation for the fiducial case or the non-perturbed case, but in both LogCal and CorrCal, the results are really good if you don't include any dish perturbations. So you can compare the result in the table to the fiducial case of about 10 to the minus 5 for both the mean and standard deviation. So the results are basically, well, you can look at the figures, but I think the table summarizes it quite well. If you take the median values for the mean and standard deviation for both CorrCal and LogCal, you can see that CorrCal does at least 100 times better, close to 1,000 times better. In the case of dimly lit point sources. So this is not including any bright sources, not assuming that we have any bright sources in the sky when we're doing our calibration. You can see in the left plot for the mean that CorrCal covers a bit of a range of mean values. These are the gain errors. So it's the recovered gain minus the simulated or true gain. And the true gain that we assume is a true gain of 1. So results close to 0 is basically what we're aiming for. So you can see that there are some runs that CorrCal sort of scatters about the wrong mean value. But overall, in terms of mean and especially standard deviation, CorrCal does seem to do better in the case of a perturbed array. If you then include bright point sources, you can see that, well, what we did in this slide was basically consider sources in the flux range of 2.8 to 4 Janskis following our luminosity distribution, and the sources are randomly scattered, and 11 of these sources contribute to the visibilities. If you compute the mean and standard deviation for the gain amplitude errors for 500 noise realizations, again using the perturbed 8x8 array, CorrCal still does better than LogCal. Another reason that CorrCal is quite ideal is you can input the known positions of the sources. So you include information on the per visibility response to sources with known locations on the sky. And yeah, so you can see that CorrCal has a lower standard deviation and mean than LogCal does if you include a few bright sources. If you don't know the locations of these bright sources, then CorrCal doesn't do very well. And the reason for that is the visibility covariance that you compute is used using the dim sources. The bright sources obviously overpower the dim sources in the visibilities. So if you give CorrCal information about the perturbed array, but don't provide information on the source positions, it just doesn't work very well. But it's still work in progress, and I still need to do a lot more work on this. But for future work, for the KSZ side, I'm currently looking at Fisher forecasts and computing parameter constraints to better understand baryon distributions. Another thing is investigating the reconstruction of modes lost due to foregrounds. On the calibration side, I need to do phase calibration for both algorithms and also test the effects of non-redundancies on power spectrum estimation using dish position errors and beam variations and whatnot. But yeah, that's the end of my presentation. If there's any questions.
Thanks a lot, Zahra. So I see there was a question from NJ, but before that, if any other students, if you have a question, please go ahead. If you have a question for Zahra. Okay, I guess not. So NJ, you had a question?
Okay, yes. So there are, the first thing is that you mentioned about the baryon, missing baryon. How does your HI-HI-kSZ 21 centimeter correlation can benefit the inference on the missing baryon?
At the moment, what we're looking into is constraining or a better understanding of the number density of free electrons, and which feeds into the optical depth, or the optical depth is dependent on the number density of free electrons. So being able to constrain tau is, I think, quite essential in the missing baryon problem.
Okay, and are you doing? If I remember correctly, you are doing like basically the these correlation, but you just mentioned the KIZ is mostly kind of on wormhole to intergalactic medium, which is pretty much on large scale, whereas the H1 is mostly locked in the galaxies. So I'm just thinking about the two scales. If the H1 is mainly just locked in the galaxies, whereas the KIZ might sample much larger scale baryon distribution, and these two correlated, but they may not correlated that much on large scale. That's what I take. And yeah. Uh-huh.
Yeah. No, we're considering that as well. I mean, we've looked at papers that basically say the same thing, that at low redshifts, there's majority of the H1 signal is contained in halos and galaxies. So there isn't a lot of H1 signal in intergalactic medium. But yeah, I can't give you a very good answer of what we would expect right now, but it's something we're considering and we know about.
Okay, and there was the other plot which you show the difference between MID, interferometry and MID dish and HIRAX. Can you reverse back to the noise curve?
Sorry, is it this one?
Yeah. I wonder. Yes, this one. Yes, I wonder. You look like the interferometry, the red curve cannot sample. I mean, there's little overlap between the dish and interferometer, but as far as I see the MID, a lot of dishes are really, in the center core, they're really close and they're really touching each other. And so would that affect, I was thinking the interferometry can sample almost off dish, because they're really close and they can sample the very large scale, the small value of K perpendicular. But your plot showing that it prohibited, at some maybe, I don't know, 5 times 10⁻². So why is that?
Yeah, the dish, the minimum baseline length limits your access to low K-pop modes for any interferometer for both SKA and HIRAX. Were you surprised about, sorry, the red curve in particular, like specifically for SKA, or was it just in general for both HIRAX?
No, I mean for Meerkat, for SKA, I mean Meerkat will be part of SKA. I remember,
yeah.
What is the minimal length that you use here, minimal baseline?
I can check in the code, but I think it might just be the dish diameter, but I may have taken into account the separation between the dishes. I can't remember right now.
Yeah, so I can also make a comment. There's no way you're gonna be able to calibrate larger than the field of view. I mean, it's going to be very difficult, these interferometers. So I don't think we can rely on access to scales larger than the field of view, and that sets this K-pop cutoff.
Okay. Yeah. So the other thing is I mean, you show this difference between LogCal, or what you call it, LogCal, or the CorrCal, the blue and red. If you reverse, if you forward to that plot. Yes. No, the previous one.
Sorry.
No, this previous. Yeah. So this one, you said so you assume a unity gain, right? And then you somehow calibrate it. So what is the mean? I mean, what is the a broad blue band called mean?
Oh, is that the question? So we plot the results for the mean of the 500 noise realizations. That's what's shown in the plot. I'm not sure if I get the question.
But what is this? But you say it's unity, and I don't see a unity here. I mean,
no, it's the gain error, so it's the subtraction. So it's the
Oh, error
recovered gains.
subtraction.
Yes,
Okay,
yeah.
okay. Oh, you already subtract the unity from this one, and
Yes, yeah.
okay. So therefore this will be the error, the mean of the error, and standard deviation would be the error of the error somehow, right?
Yeah.
Okay, yeah. Okay, fine. I finish.
Thank you.